Good morning friends. So, today is the second lecture of recursive robot dynamics. So, let us look at the summary of previous lecture. In the last lecture I have told you that why recursive dynamics should be used. I have defined the DNOC matrices. DNOC stands for decoupled natural orthogonal complement matrices, which were derived from the velocity constraints of serially connected rigid bodies. I have derived the Newton-Euler equations, two Euler-Lagrange equations, and appropriately speaking these are called a constrained minimum set. And then in those equations we have seen how the elements of the matrices like generalized inertia matrices look like. They are the analytical expression, and I emphasize the point now we would like to see the expressions as detailed as possible before we use the computer, because we would like to get a feeling, and one such situation I will explain in today's lecture. So, yesterday we got the equation of motion for one arm, that means it can be considered as a solid pendulum also. It is a revolute joint here and then this rigid link, and I will just demonstrate its numerical results using the software which is developed at IIT Delhi. It is called Robo Analyzer. You might have used for the kinematic purposes, but now I will show you for the dynamic purpose. So, I wanted to do one link. So, I choose degree of freedom is 1. So, 1 r is here. So, then I take the front view of it, and then I just take it so that it comes in the view. Okay. And so, now this is one link, and at this configuration obviously if you wanted to move. So, here it is moving from minus 90 to 90 degrees. So, I make it minus 90 to 90 degrees, and I perform forward kinematics to see its motion. So, this is the motion it performed, and I would like to know that how much is the torque required from my equation of motion. So, I perform inverse dynamics, and then I can look at the plot. Then this is the joint value, that is the trajectory for the joint I wanted to perform. This is the velocity, this is the acceleration, and these are the joint torques. Okay. Now, you can see it is more or less following the acceleration, but now this is going against gravity. Okay. Now, if you make the gravity 0, that means it is a planar motion like this, then you will see the torque will be proportional to the acceleration. So, let me make gravity 0 from here. So, here I have gravity 0, and now I perform inverse dynamics again, and then I plot the joint acceleration, and if you look at the joint torque is proportional to this thing, because it is a single link. We know the inertia about the axis of rotation is ml square by m s square by 3 multiplied by theta double dot, okay, will be the torque, because gravity now I am making it 0. Okay. So, that is why these proportional things are coming. As soon as I add gravity, the gravity term distorts this torque plot, as we have seen in the previous results. Okay. Now, when the gravity was there, if I start from some different angle, say minus 45. So, it starts from here, I perform forward kinematics, then the inverse dynamics. Now, you see the plot joint. Okay, I have not added gravity here. So, gravity is acting negative of minus y direction, and now I perform inverse dynamics, and then I see the plot. Now, as you see it here in this junction here, it is starting with certain value program for autonomous robotics laboratory. So, that kind of robot you can choose from here. So, 6 degrees of freedom KUKA robot is here. Okay. I have to run it from here. Okay. So, I choose 6 axis ok, and you will see KUKA robot will be coming up here. So, here and I take the isometric view, and here all the joints have been specified to go from 0 to 60 degree, 0 to 60 degree. I perform forward kinematics and you can see its motion like that, and then you can perform inverse dynamics. So, this is inverse dynamics, and then you can look at the plots. So, joint 1, this is the joint 1 torque, this is the joint 2 torque. Now, one thing is very obvious here, the joint 2 torque requires more torque than the joint 1. Why it is so? No, because now you look at the model, now this is the vertical axis, right, and this is the shoulder axis. Now, this guy has a cantilever action here, right. So, it has to take all the loads against the gravity, but this guy is just rotating this, much simpler. Okay. So, that is the reason the torque 1 is less compared to torque 2. So, those kind of interpretations, as I just mentioned, should be done in order to know whether your numerical results are correct or wrong. Okay. So, that is one of the way to look at the numerical results, but if you wanted to see things in a symbolic form. So, there are other tools are also available. So, here I have a tool called MuPad, which is a MATLAB product, or MuPad is independent product, but then MATLAB people use it. So, it is available through MATLAB software. So, I type MuPad here and window will come, and that one link I will show you how it can generate result for you. So, I have ready made file created. So, open and okay, it is here now. So, one link. So, exactly what I have explained in my slides. So, they are here. Okay. Now, for example, first I wanted to calculate the inertia term, which consisting of P transpose M P. So, P was E and E cross D. So, first I defined theta. So, there is a definition of theta, how to do it. Then the E vector is here, then E cross, then E transpose, then I have a D. D consists of A by 2 cos theta. So, that is coming from this fact that this link, this is my D. So, D along x axis it is A by 2 cos theta, and along y axis A by 2 sin theta. So, that is the definition I have given it. It is a matrix A by 2 cos theta, A by 2 sin theta. Similarly, E cross D. So, I define a cross product here using the component formula. So, this is E cross D. So, then I define P, then I define P transpose, then I define I matrix, as I told you yesterday that for the slender rod, now I y y I z z component will be non-zero, others will be 0. Then I define the rotation matrix, then I do the transformation here, the transformation of the inertia matrix from one frame to another frame. Then I define a matrix which is appearing as a part of mass matrix. Our mass matrix is this one. Yeah, our mass matrix is this one here, that I inertia and mass into identity matrix, and then we proceed. Then I form the mass matrix, and then I do this operation P transpose M P, which gives you m square by 3. Then I do the component of H, that is the vector of the cross product, I mean the multiplicative terms theta dot square term. For this simple case it will turn out to be 0. So, the result is 0 here, and then the final expression is here. Okay. So, in order to show you executing, since all the steps are written already, so I just show that execute evaluate all, it will do all the evaluations for you. If you wanted to change some of these parameters, suppose A you want to define as L, so you just change it here and it will compute. Okay. So, this is a symbolic way you can see the expressions to verify some of the results which you might have done it through your hand calculations. So, I wanted to introduce this tool which is very similar to Mathematica, another software. Okay. So, we have verified our results using MuPad. that equation of motion for a single link system is 1 over 3 m square theta double dot is equal to tau minus half into m g a sin theta. Now, I wanted to take you to a little complex problem, the two link system. Okay. Now, as we have seen, the general expression of our equation of motion is I theta double dot plus c theta dot is equal to tau. So, I has this structure for 2 degrees of freedom system, it will be 2 by 2, and these elements I 2 2 has the expressions in terms of our the twist propagation matrices and the twist generators as P 2 M 2 tilde B T 2 P 2. Let me go little slow here and explain the steps in detail, so that you can grasp it. And as I told you, and I am repeatedly emphasizing this point, I do not want to use computer at this stage, because my interest is to know that what are the contributions of different parameters on the dynamics of the robots. So, P 2, that means P 2 consists of E 2, the unit vector along the axis of rotation of the second joint, E 2 cross D 2, D 2 is the vector of vector denoting the mass center of the second body from the point of your joint here. So, this is my D 2. Okay. And M 2 tilde, since M 2 is the last body here. So, this is nothing but M 2 the mass matrix equal to I 2 and M 2 the identity matrix here. B 2 2 by definition one can see that it will be an identity matrix. So, now I apply this matrix multiplication here, and as we have seen for single link case, it will be E 2 written in frame 2. So, everything I am written in frame 2, that square bracket and then subscript 2 means they are the representation in that frame. Where is my frame 2? Frame 2 is this one. And how the frame 2 is set up here? The frame 2 is set up as if it is welded to the first link, means it is something like this. So, if I weld like this thing, so frame 2 is attached to the first link. No? So, I have some purpose to do that way. You might say, sir, why not first a second frame connected to the second link? No? So, it has some reasons which is explained in the book. Because of the time we are not going through that detail, but we take this fact that frame 2 will be connected to link 1 and frame 3 here on the top, that will be connected to link 2. So, here. So, this will be connected to link 2, that is our arrangement. So, having said that, so now I calculate I 2 2. So, E 2 I set up in frame 2. So, the E 2 is nothing but the unit vector parallel to the z axis. So, 0 0 1, D 2 in frame 2, that means this vector represented in frame 2 will be half A 2 cos theta to half A 2 sin theta to 0, very similar to the single axis case. Q 2, that is the rotation in this case about z axis. So, cos theta to sin theta 2 minus sin theta to cos theta 2. So, you know this. Again similar to the single link case, we transform the representation of I 2 inertia tensor of the second body, which is represented in the fixed frame, which is frame 3. Now, I convert it into frame 2. So, that will have that representation, and I 2 2 finally can be calculated as 1 over 3 m 2 A 2 square, right, because in this case
frame 2, but the moment of inertia is available as it is, because that is body fixed, right.
Here frame 3 I am putting it body fixed. For
frame 2 is explained.
Okay. So, I need to do the conversion. Okay. But again I repeat one thing, for the planar case things are not so difficult as I am showing it here, but here we are trying to build up the framework when you want to do for general 6-10 link case for example, and special cases how things will proceed. So, I 2 2 is having the same result as a single link 1 over 3 m 2 A 2 square. What about I 2 1? So, here I 2 1 is P 2 transpose m 2 tilde, but m 2 tilde is m 2, B 2 1 and P 1. So, B 2 1 is defined here, it is a 6 by 6 matrix. So, B 2 1 is R 1 plus D 2. So, it will be the following. So, B21 is this vector actually, no, it says minus R1. So, this is R1. So, minus R1 is the negative side here, and D2 is this one, but minus D2 will be just opposite. So, B21 minus R1 D2 effectively means that the vector denoting the mass center of the first body with respect to the mass center of the second body. So, again we write them in appropriate frames and then build up the equations that E2 is the same, D2 we have done it, but D2 earlier we have seen it in its own frame, and now we are converting in the first frame, and that is why instead of theta 2 theta 1 2 comes, because if I want to write in this frame now. So, this angle has to be taken into account. So, theta 1 2 means theta 1 plus theta 2. So, theta 1 2 means theta 1 plus theta 2. So, that is the definition here for theta. And then I21 will have m2 a2 square multiplied by 1 over 3 plus half m2 a1 a2 cos theta 2. So, now this variable term theta 2 comes into picture. So, finally, the complex term in this expression will be I11, the longest one. So, I11 is P1 transpose M1 tilde B11 P1. Whenever there is a repetition of subscripts here for B, it will be identity. So, B11 is an identity matrix here. Now, here I wanted to explain M1 tilde, what does it mean? M1 tilde is M1 plus B21 M2 tilde B21. I told you M2 tilde actually is same as M2. Now, what is the meaning of this? Okay. Meaning of this I will explain to you. Suppose if you rigidly connect these two bodies, okay. Suppose the joint does not exist. So, showing in this robot model, I tighten it, I welded this thing. Okay. Now, this guy cannot move with respect to that one. Okay. So, I had M2 which consisting of inertia tensor and the mass of this link. I had M1 inertia tensor of this body and the mass of this body. M1 tilde means the total mass and total inertia calculated about the mass center of this point. Okay. So, that is why we call it a composite body. Okay. Composite body means I have welded these two and they become a one body now. So, M1 tilde has this meaning. M1 tilde, if you look at one of the expressions below here, that M1 tilde is nothing but I have defined it here M1 plus M2. So, M1 tilde, once you do this operation here, you get the information I1 tilde means it is the inertia of this link written about C1 plus inertia of the first link written about C1. So, it is the combined effect. So, all the tilde expressions in these derivations means you are joining one link with another one, another one, another one. So, up to 6 links you will be generating that. So, that is the way the physics is getting developed in this dynamic process. Okay. After that, it is set of algebraic equations or some derivations you have to do it, and the final expression will look like I11 will be 1 over 3 M1 A1 square plus M2 A2 square plus M2 A1 square plus M2 A1 A2 cos theta 2. So, where you see the effect of both the links are appearing in I11. Okay. So, now proceeding in a similar manner, one thing I wanted to emphasize also here. Now, this is also recursive. So, recursive everywhere we are trying to get an recursive relation. So, even to find out the elements of the inertia matrix, I am able to derive a set of recursive expressions here. When I calculate H, I also have a set of recursive expressions here, which I have showed in yesterday's class, and then I have computed the results. Now, I wanted to show you the results for this tooling system again using the same tool as I described for single link using robo analyzer, and these are the data, the numerical numbers I have taken. The link length, the first link length I have taken as 0.3 meter, the second one 0.25 meter, the mass I have taken 0.5, 0.4 and mass center location at half. So, if it is 0.3 I have taken it 0.15, 0.25, 0.125 and IYY and IZZ. Okay. So, let us look at the results. Okay. So, robo analyzer and okay. So, two link already appeared here and it has some default values of 200, but I can change it to the length I have chosen, that is 0.3 meter, that is 300, and the next one is 250. So, 250 and I can come here to change my link parameters. So, mass center location was 0.15 and then mass properties, mass I have taken as 0.5. So, mass is 0.5, then I XX IYY it was 0.00375, 0.00375 and the next one will be again 0.0375, that is for the first link, and then for the second link I go down. So, for the second link mass was 0.4 and that was 0.00208. I have selected here, okay, and I do not have to select from the window, it is only from the input panel. Okay. And oops, okay. So, now I perform forward kinematic, that result can be seen, okay, and then I do inverse dynamics and I see the plot, and the joint value was varying like this, and this is the joint torque. Again since gravity is acting, so you are starting from a non-zero value. If you switch off the gravity term, now in this case which one will have a larger torque, 1 or 2? 1, right. So, let us see whether it is having. So, this is second one and the red one is the one. So, obviously, the first one has to carry the second link, the first one will require more torque than the second one, and which is coming here. Okay. Okay. So, these are the plot I have shown you here also. So, if you have no gravity, then it is as if like the link is moving in a horizontal plane like this one, okay, and the plots will be proportional to the acceleration, at least for the second link, and the bottom one is for with gravity. Okay. Now, so far what we have discussed is actually inverse dynamics. So, if I write it here, we had these kind of expressions I theta double dot C theta dot, which we have also denoted with H is equal to tau. But when gravity is coming into picture, one can also think that this tau is consisting of tau external or the actuator and the tau g, something like that. Okay. And what we have done so far, we have provided the input theta double dot, that means I know how my robot should move. I have provided theta dot, I know what velocity it should move. I is a function of theta and mass, link length, etc. So, for a given system they are also known. So, I know this one. Similarly, C is a function of theta and theta dot and mass, link length, etc. So, all those are my input parameters. So, that are also known. I know whether gravity is acting or not. Okay. So, finally, what I have calculated is this one. So, this is my inverse dynamics. In forward dynamics, my problem is just the opposite. So, I have this equation of motion tau A plus tau G. Now, here I would calculate theta double dot first. What are the things known here? System is given, so mass, inertia they are known, but theta I do not know where it will go. But what I am providing is I am providing what will be my joint torque, and then I want to calculate what would be my theta, theta dot, theta double dot. So, the problem will be formulated as follows. So, it will be I inverse tau A plus tau G minus H, and then what we will do is we will then integrate further integrate, we will get it. Now, so it is a solution of differential equations. So, what we have to do for that, what we need is the initial conditions. So, given the initial conditions theta and theta dot at